So okay, this is the table for the important properties of semiconductor. See, there are lots of properties available, or lots of properties are could be listed out, but I've only shown those many properties which actually we should remember, or we should bear some values in our mind, so that we, for any problem or for any scenario, we can understand in both the ways, intuitively and quantitatively. So therefore, the very first one is atomic density. So it tells us the number of atoms per centimeter cube. Now you can imagine 1 centimeter cube or 1 cubic volume is very small amount, and within that there are 10 to the power 22. We should remember this figure at least. So there are 10 to the power 22 number of atoms per centimeter cube, and it is same for all. So mainly we have to concentrate in these two elements, and we have to conclude the supremacy of silicon. So that is the objective of this topic. So if you see all the three elements, or all the three possible semiconductors which we are basically highlighting, they are tightly packed with the atoms. So therefore they are found in the solid state. They are hard crystalline material. So out of 10 to the power 22 for silicon, we have understood that only 10 to the power 10 covalent bonds have been broken. If one covalent bond is broken, then one electron is free and one hole is free. So therefore the very next one is intrinsic carrier concentration. Carrier means free carrier, that element which can transport the charge or transport the current, which can carry the charge. So that is a free hole or a free electron. So this value is for both. So these many number of electrons or these many number of holes are free holes and free electrons are available in the silicon out of so many atoms. So again, I am reminding you that this figure may appear misleading because it looks a large figure, but this is negligible in front of this. So this is a very poor number at room temperature. So if you see at room temperature, this is the free carrier concentration. So these many number of electrons and these many number of free holes are available in the conduction band. So they are ready to move and they are moving randomly. But because this is a very small amount, as I am saying, so we cannot get an effective current or a sufficient current out of it at the commercial applications. So for commercial applications, this concentration must be somewhere of the order of 10 to the power 14 or 15. Then we can achieve some good current density. So this example I'll be showing later on, but so far we should bear in mind that this, for germanium, this is little bit higher, not little bit, in fact this is 3 order higher. So this point appreciates the supremacy, or this tells us that germanium is a better material in that case, but there are various points which will prove the supremacy of silicon again. Similarly for gallium arsenide, we can notice melting point. This is an important point. You see that the melting point of silicon is highest. So this point and one more, this point, band gap. See, a higher band gap and a higher melting point. These two things make a material very suitable for high temperature stability and high temperature applications. So if you have to do some processes like oxidation, rapid thermal annealing in the integrated circuit fabrication, in integrated circuit technology, then a material should withstand with those processings. If it gets ruptured, if it melts out, then it's of no use. So we are looking for a material which can withstand with 1200 degrees centigrade or 1300 degrees centigrade processes. So that we can see that melting point of silicon is very high. So therefore it proves to be a higher temperature stability. Means a high melting point oblique a high band gap. EG is a shortcut of band gap, EC minus EV. So a high melting point, a high band gap corresponds to a higher temperature stability. So therefore silicon proves to be the excellent material for lots of integrated circuit manufacturing processes, and therefore it's the best choice. Then we can see the crystalline structure is diamond. For germanium is also diamond. This is zinc blende. There is a slight variation, slight modification from diamond to zinc blende, but basically all these are the some examples of simple cubic or cubic structure system. So we should just remember the name. The other details could be understood in detailed crystal theory, which is not under the scope of this course. The dielectric constant again we can remember, and a higher dielectric constant means the better conductivity in some rough sense. So that also we can remember for lots of mathematical calculations. Band gap we have already seen. We will be looking at this point and these 2 points very frequently in lots of numericals. So these 3 points are very 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 frequently used in the numericals. And last point is also very very important. This is also very frequently used in numerical. This is the mobility of free carriers. Though we shall be defining this term mobility in detail after some time, but for now it is only important to understand that mobility is the easiness of motion. So if two particles are getting the same influence, same force externally, but if one is highly mobile, one is not that much mobile, then the highly mobile particle will move much rapidly with much velocity. So that ease in motion is indicated by the mobility. So the mobility of free electron in silicon is this. The mobility of free hole, because only free electron and free hole can conduct, so the mobility corresponds to the free carriers only. So for free hole the mobility is 480 centimeter square per volt second. The unit is also very important. In most of the public sector examination it has been asked. So these two is the value, this two is the value for electron and hole mobility in germanium, this is the electron and hole mobility in gallium arsenide. One very important observation we can notice that from any of this pair we can see the electron mobility is always larger than hole's mobility anywhere, be it silicon, germanium or gallium arsenide. Let's be this. So generally the electron mobility is 2.5 times larger than mu p. So mu n by mu p is 2.5. You can make this ratio. So if mu n is greater than mu p, it tells us that a free electron moves much rapidly than a free hole if the same force, same electric field is applied. So high velocity of an electron means a larger current, a higher current. So the devices which are basically consisting more free electrons rather than free holes are highly favorable as compared to those devices which have dominant particles as free holes rather than free electrons. So we, in the whole course of electronics or in semiconductor electronics, we shall favor those devices which have the majority carriers as free electrons rather than free holes. So this is a natural tendency, but still those devices which are having majority carriers as holes are also in of great use, but this is the general trend. So this is one observation, and another observation is, if you see here the ratio is 2.5, here the ratio of mobility is 2, here the ratio of mobility is 20. First of all, as we have declared that high mobility means high velocity of particle and a larger current. A larger current corresponds to fast motion, high speed device also. So therefore, if you see, this value is very very high, which makes gallium arsenide highly suitable for high frequency applications. Now high frequency applications include microwave, switches, etc., and other high frequency applications like, for example, pin diode, trapet, impet. We are not going into the detail that we will be looking on later. But for the microwave applications, when we come out of these devices, tunnel diode as well, then all these devices are generally or dominantly made up by the material gallium arsenide. Because of this nature, the very very high mobility of electrons, they can move very rapidly, they can respond at very fast pace. So this material is highly suitable for that. But still the excellent nature of integrated circuit manufacturing technology, we still exploit the mobilities of silicon. So silicon is still in use for high frequency application, but we would like to prefer this gallium arsenide. Also, if you see a higher mu n by mu p ratio, if mu n by mu p ratio is high, then this kind of nature is suitable for switching applications. Where we have to make on and off kind of scenario in high frequency digital circuits, where we have to rapidly make on and off. So with high frequency, if you have to make switching application, then mu n by mu p ratio must be high enough. So that is found with the either with the silicon or with the gallium arsenide. So gallium arsenide again proves to be the excellent material for the high frequency switching applications, but for low frequency as well as for digital applications, if we are looking for switching phenomena, then we prefer silicon over germanium. So again, silicon proves to be superior than germanium for this point. So with all these points, we can remember lots of theoretical questions which are generally asked in public sector examination as well as in GATE. Now the band gap, as we have understood, is if this is the conduction band, which contains all the energy levels or the corresponding energies of those electrons which have become free, which have become unbounded from their atoms, from the covalent bond. And this is valence band. It indicates the energy of those levels or energy of those electrons which are still valence or which are being shared in the covalent bond, and they are not free to move within the material. So this is valence band and this is conduction band. There is no finite edge defined or absolute edge defined at the lower end of valence band. Similarly, there is no finite upper end defined for the conduction band, that we have already seen. So the lowest value of the conduction band is EC, the highest value is EV, and this, as we have seen, this is band gap. We indicate it with EG, EC minus EV, and we'll measure all these things in the electron volts. So this band gap table says that if I write it let's say for metal, for silicon, for germanium and for gallium arsenide, or let me write it also for insulators. And let us only focus some important temperatures. The very first important temperature is absolute zero, means T is equals to 0 Kelvin, or room temperature. So this one is called absolute zero, and this one is room temperature. So for almost all applications, we'll have to consider the room temperature. So practically we'll be only interested in room temperature, but if we see all those properties at absolute temperature, then we understand how the property has progressed as we have moved above the absolute zero, and we basically fetch some information about that property or its trend as per temperature changes. So this gives some better idea if we compare the property at both the temperatures, although we do not have to make use of this temperature anywhere in our practical life, but it still gives us a trend that how the property changes when temperature increases. So for metal, actually we are not strictly defining band gap, but still, as I said, that for comparison purposes we mark the same valence band and conduction band for metal, but there is no such scenario within the metal, or there is no such kind of conduction and valence band strict definitions possible for metal. So we keep it undefined, or let's take it 0, because both are merged in some or other way, and almost all the carriers are free always. So they are free, but their thermal energy is 0 at room temperature. So even if all the carriers are free, so all the values are in electron volts. So for metal it doesn't matter. Even if you increase any temperature, you go for some 300, after that you go for 400, 500, 600 Kelvin, degree Kelvin, you keep on increasing the temperature, but the valence and conduction bands are already merged, or we must remember that there is no difference, or there is no band gap existing. So almost all the carriers, or plenty of carriers are always available to transport the charge. So therefore this is the scenario. For silicon we have seen the standard value is 1.21 electron volts. For germanium at this is 0.785 electron volt. There may be some variations as per different literatures at the second point of decimal or the third point of decimal, and that also happens because strictly the values, the very accurate values, depend on how the crystalline format or the crystalline form of semiconductor has been processed, how it has got developed, so how much pure it is, and its orientation and a lot of things. So therefore we should only keep our concentration, or we should only mind the up to the second place of decimal. And then for gallium arsenide this is not very well known, so I'll not mark it. For insulator generally it lies somewhere around 10 to 15 electron volts. This is also not very strict, so I have written a range. Generally we are interested in these two. For metal, again, as we have already seen, that it doesn't matter if temperature increases, there are still a lot of carriers available as they were at the lower temperature. For silicon we should see the value go around 1.12 or 1.14 electron volts. This becomes around 0.67 electron volts. This comes somewhere around 1.42 at room temperature, and this insulator value has got down around 6 to 12 electron volts. So again, this is not very strict, this is a rough idea that how large a band gap is. But if you see this from this table, as well as I'm going to write a relation, it becomes clear that band gap is a function of temperature. How is it a function of temperature? Let's see. E.g. band gap is like at any temperature, present temperature T is E.g. naught. That means at T is equals to 0 Kelvin plus, minus constant beta into T. Where for silicon, for germanium we can write the values. For silicon, E.g. naught is at the absolute 0, the values we can fetch it from this 1.21 electron volts, and E.g. naught for germanium is 0.785 or 0.78 only. Beta, if you see, this is the absolute temperature, this is beta into T. So beta is the rate of decrease of band gap as temperature increases. So from this equation it is very clear that band gap contains this kind of profile. So if it is EGT, if you want to plot it, so there is no temperature defined below 0 Kelvin, so because 0 Kelvin is the absolute 0, so this third or second or third quadrant, it doesn't exist. So we'll have to only plot from here, somewhere from here, like this. So this one is 0 Kelvin and we are somewhere here. at room temperature 300 degree Kelvin. So you see, this is the constant line, so it decreases, but it decreases very slowly. So this thing comes from the value of beta. If you see, beta for silicon is around 2.2 into 10 to the power minus 4 electron volts per degree Kelvin, and beta for germanium is around 3.6 into 10 to the power minus 4 electron volts per degree Kelvin. So with these values we can calculate the band gap at any temperature above the absolute zero, or even if you want to calculate it at absolute zero, we can very easily see that it is only Eg naught. So with this value, if you see beta, that it's a very small value, so therefore band gap is a function of temperature. It decreases as temperature increases, but it's a very weak function of temperature. So I must say that Eg T is obviously the function of temperature. As temperature increases, then Eg decreases, but it's a weak function. So the decrement in Eg is not very significant. So let us understand with an example. So let me take one example here itself. Let us calculate the band gap Eg for silicon and germanium both at room temperature first and at T is equals to 600 degree Kelvin. So let us calculate it from this formula which we have just described. So you see, this is not a very tricky one. I mean, simply you have to keep values and you have to get the answer, but this is to understand the range of band gap or the range of temperature, how much it affects. So let us again calculate at room temperature first. So at room temperature, T is equals to 300 degree Kelvin, and from this Eg for silicon becomes Eg naught minus beta T. So Eg naught is 1.21 electron volts minus beta is 2.2 into 10 to the power minus 4 into 300. So this is already in electron volts per Kelvin into this much of Kelvin room temperature. So one can try to find it. It comes around approximately around 1.14, which we have already listed out here. So you can cross check it. I have already calculated it. So it comes around this value at room temperature. So it's verified from this. Similarly, if you try to calculate Eg for germanium, then it is 0.785 minus 3.6 into 10 to the power minus 4 into 300. So at room temperature, this comes around 0.67. That also you can calculate. So I have already calculated and it comes around this. Similarly, if you calculate at 600 degree Kelvin, 600 degree Kelvin means a temperature 300 degree Kelvin above the room temperature, or 300 degree centigrade above the room temperature. So please keep in mind that the change in temperature in degree Kelvin is same as in degree centigrade, because the difference between these two units is an additional term, not a product term. So any change in temperature would remain same whether it is in Kelvin or in degree centigrade. So anyhow we have to keep only in Kelvin here. So at this Eg for silicon at 600 Kelvin is around 1.21 minus 2.2 into 10 to the power minus 4 into 600. So this thing will be replaced by this. So if you try to calculate it, this 1.078 electron volt. You can anytime calculate it using your calculators, and Eg germanium is 0.785 minus 3.6 into 10 to the power minus 4 into 600, and that also comes around smaller value, somewhere around 0.5, comes around 0.569. So now if you see at room temperature, let us only concentrate for silicon. This is this. This is this. So you see, when temperature changes by 300 delta 300 degree Kelvin. So if temperature goes above the room temperature by 300 degree Kelvin or 300 degree centigrade, so this is a huge change. A human person cannot think of that much change, and we cannot cope up at that temperature. So you can just imagine that. So when we go up to this temperature at 600 degree Kelvin, the value is this. So you can see there is only a very marginal change. The change is not very significant, although this much change influences a lot for the carrier concentration, which we are just about to see after a few minutes. So but still the band gap decreases very slowly, or it's a weak function of temperature, which we already argued by observing the value of beta. So this numerical is only for some data in our mind. So but practically, in the practical scenario, the temperature changes within 10, 15 or 20 degree or 30 degree centigrade, or 15, 20, 30 degree Kelvin in the practical considerations. So we can assume that for these many temperature fluctuations in this range, the band gap decrement would be almost negligible. So we always keep it like a constant at room temperature and around room temperature, even if it increases or decreases by 30, 40 degree centigrade or 30, 40 degree Kelvin. So we'll assume that value intact with this 1.1 electron volts and 0.6 or 0.67 electron volts. Okay, so one more small point, a general point about the energy band diagram, where K is basically the wave vector, and this comes from the Schrodinger wave equation, or from the brilliance zones within the crystal and crystal theory, and it comes from the crystal theory. So we need not to go into the deep of it, and we just have to briefly cover what does it say. Basically tells us that there could be two types of band gaps. One is direct band gap, another is indirect band gap. So direct band gap is, let me call it like this, direct band gap materials and indirect band gap. So let us draw some picture about that. So this picture, let me first discuss with you that this picture of EC, EV and band gap, so this picture, what we generally show, is not so simple, or it's not like this exactly. As I briefly discussed, that there are lots of discrete energy levels and different energy levels which correspond to different energy particle, like electrons in valence band, similarly electrons in conduction band. So the energy levels are not so simple, so they are randomized in fashion, and the actual picture or actual scenario is something like this. So there are different zones of bands like this. So all these zones they depend upon the energy experienced by the electron which moves within the crystalline material. So any electron, when it moves within the crystalline material, is governed by lots of energy, with the experiencing from the atom itself, from the some neighbor electron or hole itself. So it experiences lot of energy. So its energy profile and its wave vector profile is not so simple, it's highly complicated, and we should understand that this whole blue color and this upper one is the conduction band, and this one is the valence band, and definitely they are not so simple. So the lowest value of energy and the lowest valley in the conduction band, which is indicated by this, we mark a line over here if this is the lowest valley possible, and the highest peak or highest valley inverse of valley, I'm sorry, is this in the conduction in the valence band. So we mark it like this. Another discrete energy level in the valence band, if you want to show, then it would be this. Then the just lower one would be this, and then just lower one would be this. So the highest value of these energy zones would be indicated like this. And similarly here, if we have to mark energy levels, this like this, and then these levels are fairly very close to each other, so the gap between any two discrete levels, this is much smaller than the band gap. So it may not be very clear from my diagram, but generally this gap between the highest energy level in the valence band to the lowest energy level in the conduction band, this gap is the largest one, and it is so high so that these small gaps are almost insignificant, or they are not very visible. So if you look at roughly, then it appears like this lower side is a band, this upper side is also a band, but actually it is not a continuous band. There are discrete levels in both the valence band and in the conduction band. So when we see this scenario, and these energy valleys or profiles, they depend on lots of things, the energies or the wave which is associating with a energy particle, or with a current carrying or charge carrying particle like electron, and it depends on the wafer orientation. So it comes all from the Schrodinger wave equation, and then they are called different zones, like Brillouin zones. So this diagram, horizontal diagram, is generally a wave vector k, which also locates or fixes the space location or the 3D space location of an energy particle. So therefore this horizontal direction, as we can write it, wave vector k, or the momentum vector. Momentum is you see, is governed by a lot of things. Again, from the major thing is the crystal orientation. So for different orientations, it is different. Now we can understand the crystal orientation from the detailed crystal theory, but all of us are at least aware of some very popular crystal orientations like 100, 111, 001, 110, and a lot of different crystal orientations. So maybe this may correspond to some 111, this one may correspond to some 100, this may correspond to some 110 or something. So therefore this picture is a crude approximation of this. So most of the time we need not to have this much of detail, only this much diagram or this approximation is sufficient enough. But when we have to understand the direct and indirect band gap nature, then we need to understand this profile. So after this we can see what direct band gap means is something like this. So let's say this is the profile of some material where this is the lowest valley in the valence band. So the horizontal level corresponding to that will be called the conduction band edge, EC, and then the next one is arriving somewhere here. We are not really bothered about the higher energy levels, we just wanted to locate the lowest energy level in the conduction band, because that is the conduction band edge indicated by EC. But if you want to understand others, if this lowest energy valley or this horizontally coincides with the or it appears in a straight line with the highest energy peak in the valence band, like let's say this, then, and the next one is this, the next one is then next one is this. So if you see, the highest peak in the valence band, which is defined by EV, coincides with the lowest valley in the conduction band, which is indicated by EC, and they coincide in the on the horizontal scale, on the momentum vector scale, or the space vector scale. Then this kind of band gap is basically called the direct band gap. And in that case, when any recombination happens, recombination is just the reverse process of breaking of a covalent bond. In breaking of a covalent bond, the energy is being absorbed by some covalent bond, and it is being or it is making one electron hole pair free. So that is called generation of free carriers. When the reverse happens, the free electrons and free holes are randomly moving within the material, within the semiconductor material. If they find some favorable condition and they come close to each other, they are willing to terminate their existences, and they are willing to recombine. So as soon as they recombine, they lose their existence, and this process is called recombination. So whenever there happens a recombination, an already free electron somewhere from here, let's say, or somewhere from here, comes down like this, and it occupies this energy state, means an electron finds a hole and it recombines, and the existence of both is vanished. Then that happening in the that thing happening in the atomic structure is understood by same as one electron has moved from the conduction band level to some level somewhere in the valence band. But all because there is a direct band gap, then this process may happen directly or vertically. There is no alignment of momentum vector required. So please mind, there is no alignment of momentum vector required. So momentum is not transferred to the lattice space. This whole momentum gets collapsed when both the electron and holes are combining with each other. So when the momentum is being collapsed, and this momentum is being released in the form of photon. So this energy or momentum is translated to energy. When this comes out, then this is the energy which corresponds to either this minus this or this minus this. It depends from what level the electron has gone to what level in valence band. So some energy h nu, this nu is only the frequency, and this is called the photon emission. And from the optical theory, some basic optical theory, we all know that when a photon is emitted, then this frequency actually falls in the optical range. So this frequency falls in optical range, and then only we call this hypothetical particle as photon, which is a quanta of light energy. So therefore, in such material where there is a direct band gap, whenever a recombination happens, some energy is released, and that energy falls in the range, the corresponding frequency falls in the range of optical frequency or optical light. So therefore such kind of material could be utilized in the opticals, or in the optical communication, or in optoelectronics, or in those electronic applications where optical phenomena is required, where the light phenomena is required, like LEDs, like laser diodes, and lot of things. So the example of such materials are, the very popular one is gallium arsenide. So indium arsenide, cadmium telluride. So please remember, these materials, they have the direct band gap nature, and therefore a recombination process within that material is translated to an optical emission or photon emission, or they find extensive applications in the optical communication, or in the optical electronics, optical semiconductor electronics. Whereas in the case of indirect band gap, they are the lowest valley in the conduction band is not aligned horizontally with the highest peak in the valence band. So this picture may be something like this. So let's say this is the the lowest direction. This goes like this. So in such kind of scenarios where the highest energy possible or highest peak in the valence band is this, so this corresponding energy will be EV, and the corresponding energy to this lowest peak in the conduction band will be EC. Then you can indicate other levels also, but we are not interested. And this direction, as we have already discussed, is the K momentum direction or vector space direction, K space vector direction. And let's say this side we indicate some 1 orientation, or to this side is the some 1 0 0 orientation. So similarly, depending on the wafer orientations, we have different momentum vectors defined onto the horizontal scale. So when this scenario happens, then we can very easily see in this case that whenever there occurs a transition from conduction band to valence band, that means whenever a free electron is finding a free hole in the close proximity, and when they are going to recombine, then that momentum is not similar, and that difference of momentum, this horizontal, that difference of momentum will be transferred to the lattice, and there will occur a lattice vibration, and therefore a hypothetical particle parallel to photon, we call it phonon here, is emitted. So therefore, if a recombination has to happen, then this difference particle has to emit, and this will be called as phonon, and then this thing happens. So it doesn't happen directly. First of all, the momentums have to be aligned, or they are not aligned already, so they have to be aligned, and in order to do this, the difference momentum is transferred to the lattice. So there happens a lattice vibration, and due to that a phonon emission takes place, and therefore the energy this time which is released due to this recombination doesn't fall in the optical range, and therefore it is not finding any application in the optical electronics or optical semiconductor electronics. So there is no such particle like photon exists here. Hypothetically, again, we assume that due to this momentum conservation, due to this difference of momentum, there happens to be a emission of a particle called phonon, that results due to the difference in momentum. So with that we can conclude that there is no such photon emission. So and this effect is all attributed to this fact that the there is an indirect band gap structure. So this phenomena is called the indirect band gap, and the example materials are very popular: silicon and germanium. Please remember, silicon and germanium are indirect band gap materials. So in silicon and germanium, if recombination happens, we all know that we cannot directly find their applications into the optical electronics or in the optical range. So but you see, all third, fifth column combinations are not having direct band gap nature. Like I've written gallium arsenide, indium arsenide, and cadmium telluride is very popular in commercial applications, but not all combinations like aluminum phosphide, like some other, they all are not the example of direct band gap material. So do not take it like in general all the third, fifth column combinations are direct band gap example. Gallium phosphide and aluminum arsenide, they are basically indirect band gap examples. So although they have third, fifth column combination, but they are not direct band gap. So this is some internal behavior, and we need not to understand why exactly this direct band gap or indirect band gap is happening. But if it happens, it differentiates the material in lieu of the application in the optical electronics or in the optical field. So we should remember these examples because they are very frequently asked in most of the public sector examinations, or possibly in GATE also. So let us finalize this topic general points by concluding the advantage list of silicon. So the question which we put a Y silicon. So let us finalize the points, and basically we are looking at the advantages of silicon specifically over germanium, but this list is not only restricted for these two comparisons. This is in general the advantages of silicon, but at some points we are generally comparing it with germanium also. So the very first point, you see there are lots of points possible, 6, 7 or 8 points, but I am writing these points in the preferential order. Means the most dominant point, the most dominant reason why silicon or why silicon is beneficial over germanium or beneficial over other semiconductors, the most dominant point will be the point number 1, and then second and third, because still in lots of public sector examination or in GATE, this question is asked repetitively in some different format. So, and there may be in some public sector examination, there may be more than one choices possible which are correct. Then we have to tick or we have to mark for that answer which is the most dominant reason for this. So therefore I have listed out, I am going to list out the reasons in the dominant priority. So the very first reason is the abundance in nature. With this you should remember that it is found in the format of silica. Then with silica we basically develop EGS, electronic grade silica or electronic grade silicon, which is a pure, very high quality silicon, but in the amorphous form, in the polycrystalline form, and then we again process it to obtain single crystal silicon. So by just saying abundance in nature should not be taken as the single crystal or the pure crystal silicon is directly available in the nature, but the crude form of it is silica is readily available in a huge quantity, and it has been assumed that for some 50 to 100 years we will not get shortage of this silica, and will still with the same mechanism will be able to develop the single crystal silicon out of it. So this process takes a lot of effort and time, but in comparison to other semiconductors, this is still, we have achieved a lot of maturity, lot of expertise in this process. And the in my opinion, the second point which I am going to write is more dominant than the first reason, but it's still some UPSC examination or some public sector examination, they still feel that point number 1 is more dominant, so I have written it like 1. Otherwise these 2 points are equally important, equally dominant. The point number 2 is its well support to IC technology. So this is not a very standard term or standard line, it needs some explanation, like there are lots of things to explain this. It gives very well support to IC technology. The very first point makes a lot of things clear, like if you see a silicon in its original form in the single crystal form, if it is single crystal, it is actually a semiconductor. Okay, so most of the time we have to start a wafer, an integrated circuit at the base level, it should be a good semiconductor, so therefore we utilize this nature. Then its another form, if we take its amorphous form or polycrystalline form, then a polysilicon, we call it polysilicon, is basically a better conductor as compared to this, and the conductivity could be increased by some better processing schemes, but better technological schemes, but polysilicon is definitely a much better conductor than semiconductor, than the single crystal. So if it is well crystalline form, then it is this, but if it is some by amorphous or polycrystalline, you can think that it is not a single crystal crystalline behavior maintained, it's some powdered form of it, something like that. So then it is a conductor, not very good but a better conductor, and we can make it a better conductor as well. So in most of the recent technologies where we basically want to have a metal layer to connect to make a connection between two different terminals, then most of the time nowadays we skip that metal line and we make use of polysilicon. And third form is if we take its oxide, then the example is SiO2, and this is very good insulator. And I think out of these three, this thing is very, very important. So already we know, we need not to highlight this point, we already know that we have started using silicon all because of this nature. Then this most of the time we may be looking for some interconnects, for some connections, then we can skip metal and additional material onto this. And whenever we need some insulator, then again we can exploit the silicon. So what if the silicon is found in all three formats, or we can develop all three natures out of a silicon? This point becomes important because whenever we are going to develop some circuit, some device within a semiconductor like silicon, then let's take an example of MOSFET, then we may be looking for all kinds of materials or regions like a metal, oxide and semiconductor. Metal means we should have a very good conducting material, then below that we should have a very good insulating material or a dielectric material, then at the base end we should have a relatively better conductor than insulator, that is a semiconductor. So a semiconductor and metal, and in between there is a dielectric, so this makes a MOS structure, metal, oxide, semiconductor. So specifically for MOS or for FETs, this nature of silicon, that it has been found or it could be developed in all three formats, this property has been exploited in a great extent. So means already at the base we have silicon, so if any time we have to grow an insulator, then we would not rely on any other insulator, and or we will be going for a insulator which is developed by silicon itself. So already we have a silicon, and on to top of that, if we want to grow an insulator, we can very easily grow silicon dioxide, SiO2. So it supports, it gives a good mechanical stability with the base material, it gives a very good chemical bonding with the base material, it could be effectively developed, it could be effectively controlled, the thickness of SiO2. So lots of benefit we can achieve if we are depositing, if we are developing some oxide layer or some insulating layer which is formed by the base material itself. Then again on to top of that, if we have to make some connection or some metal layer, then again we need not to introduce some third particle or some second particle or some second material, we still can take benefit of silicon. We can make use of polysilicon. Again, it gives a good chemical bonding, it gives a well support with the pre-existing silicon at the base. So this kind of nature could be highly exploited in those technologies where very frequently we might look for different material properties like insulating property, semiconductor property or good conducting property. So therefore this reason is very strong. So this has benefited MOS technology in a great extent. MOS technology. MOS is a shortcut or short form of MOSFET. So this is very important point. Third is that there is low leakage current in pn-junction diode. So whenever you make a pn-junction, not only a diode, in lots of other complicated devices or higher devices like BJT or MOSFET or JFET, we most frequently encounter with the PN junctions are always there. So whenever we have a PN junction within the semiconductor, then that PN junction would relatively consist a lesser leakage current, lesser reverse saturation current that we will learn in the diode, but with some prior knowledge we can appreciate this point that a reverse leakage current is never required. We are not looking for this current ever. So we always want to have the reverse leakage current or leakage current as small as possible. So this point actually appreciates the benefit of silicon at least over germanium, because for germanium the reverse leakage current or leakage current is much more. Then high temperature stability, we have already seen this. This point is attributed to a relatively larger band gap as well as a higher melting point. Then high power handling capacity. So devices made up by silicon semiconductor, they have a relatively higher power handling capacity as compared to germanium or gallium arsenide. And then we can also mention economical processing techniques, means IC technology we are again mentioning, means this point is somewhere related with this. Means it has been seen that with silicon, silicon finds lots of application in integrated circuit manufacturing, and it is all due to the fact that silicon's chemical, physical and electronic behaviors are very well suitable for the lots of IC manufacturing processes. So due to this reason also, and due to lots of other well supportive nature of silicon material, it is very well suitable for the processes through which we develop an integrated circuit, at least in comparison to germanium or gallium arsenide. So still silicon has become the best choice for any semiconductor material or any semiconductor device fabrication or development. So with this, all the theoretical points have been almost completed. We very quickly will see one numerical which will refresh our understanding of this course, or sorry, for this lecture. So okay, this is the problem. It tells the longest wavelength which could be absorbed by silicon, which has the band gap of this, is 1.1 micrometer or micron. If the longest wavelength that can be absorbed by some another material is this much, then find the band gap of that material. Now we have to understand that how the absorbed wavelength is related by the band gap. So it's very simple. We have seen in modern physics, with some prior knowledge, we all know that if the longest wavelength is absorbed by the silicon, which has the band gap of 1.12 electron volts. So if this is being absorbed, and this energy we are saying h nu, not photon, but anytime we can represent the incoming energy as h nu, where h is the Planck's constant and this nu is the frequency. So we can write it hc by lambda, because frequency is velocity by wavelength, and the velocity for such a case is always the velocity of light. So it is hc by lambda. So this energy is coming here to absorb this. Now you see, the minimum energy required here for the absorption should be this. So if at least this much energy should be there, so this energy should be at least greater than or equal to Eg, which is 1.12 electron volts. So therefore, if we write lambda should be less than or equal to hc by Eg. So obviously, if we see lambda has to be lower than this value, then the highest lambda is hc by Eg. So lambda max is hc by Eg. Now this whole is for silicon. So silicon, H and C are constant, Eg is for silicon. So this is equation number 1. If the same scenario is there for some other material which has maybe some wider or some lower band gap, that's what we have to calculate. We do not know what is the case, but let's say there is some another material Eg, some another material M. So for that, if we write, then lambda max for that material M is equals to hc by Egm. So if we divide these two equations, 1 divided by 2, then generally, actually, what we are doing in this case, we do not want to keep the values of h and c, and we do not want to make the mathematical complications. So when we divide these two, we need not to have the Planck constant value or velocity of light value. So these two things will cancelize each other. So lambda max for silicon upon lambda max for that material is equals to, so this divided by this will make EGM upon EGSI. So EGM band gap of that material upon band gap of silicon. So out of that we have to calculate this. So EGM is EG of silicon into lambda max for silicon upon lambda max for that material. Now we can keep the values. It has been given from here itself. You see, if lambda EGM corresponds to this, this corresponds to this. So if the band gap is larger, then lower would be the lambda max. So in this case, if we see, the maximum wavelength for silicon is this, the maximum wavelength for that material is this. So if this is lower, then we should expect a larger band gap that we are expecting. Let's see what comes from there. So EGSI is 1.1 micron. That is the unit. Sorry, this is not EG. EGSI is 1.1 electron volts into. This is 1.1 micron for lambda max for SI, and lambda max for that material is 0.87 micron. So this will directly come in electron volts. So EGM, if you calculate, it comes around 1.416 electron volts. So this is the answer. So as was expected, the band gap is larger. So for a larger band gap, if we have to overcome this, we are looking for some energy which should be larger. So if this energy has to be larger, this lambda max has to be lower, and that was the case. The lambda max for that material was lower than the lambda max of for the silicon. So it is consistent with our theoretical analysis. So now come to the next problem. This also has appeared in GATE examination, as the previous one also was there. So in this problem, a charge distribution in a metal dielectric specimen, metal dielectric and semiconductor specimen is being given. So this side is metal, dielectric and semiconductor. So there is a combination, there is a sandwich. The negative charge density decreases linearly in the semiconductor. So here there are lots of negative charges and the density decreases. So there are less number of charges, or the density is reducing from x2 to x3. The electric field distribution. So what would be the electric field distribution within this? So we can start it with 0 here. So out of 4 options, we have to select the best option. So you see that this has to just deal with the phenomena, with the fundamental concept that within the metal, because there are lots of free carriers to respond to an electric field. Please remember, whenever in an electrostatic for electrostatic situation, we need to have the charges to be static. If within an electric field the charges can respond to it, then that electric field cannot be sustained, or that cannot be static. So if the electric field is due to the charge distribution system, where the charges itself are responding, they are moving, or they are free to move, then that electric field will not be maintained. That's what happens within the metal, because we have already seen that within the metal there are plenty of charges which can respond to the electric field. So electric field is never sustained within the metal. So it only appears at the surface of the metal, or it comes out of the metal. It is not inside the volume of a metal. So therefore it has to be 0 within this. So this option is not correct. This option is not correct, because from this to this one, from this to this one, they show some electric field within the metal. It cannot be there. Now the electric field will be sustained within the dielectric, because within the dielectric there is nobody to transport the charge. So this is like a parallel plate capacitor, like there are some charges, some a charge Q system, some minus Q system, and this side is some plus Q dash system or something, possibly to be equal. So and within this there is a dielectric, so in between there is no possibility of current transport, because there is a dielectric until unless you apply some force. So within a charge free region the electric field remains sustained. So within this the electric field has to be sustained. So this option is not correct, because the electric field cannot vary within a dielectric, because within a dielectric there is nobody to conduct that electric field, so its effect will be maintained. So obviously this is correct one, because up to this the electric field is maintained within the dielectric, and because charge density is decreasing, there are more charges, then lesser charges, then less charges, then less charges. So if there is a charge variation, there has to be the electric field variation. Now please remember, there are not so many charges as they are available in the metal. Maybe from the diagram it is not quite visible, but in the metal there are lots of free charges available. There are not very free charges available to the semiconductor, so they can still not respond a lot to the electric field, but in some sense they can respond also, but not too much as they were in the metal. So therefore there has to be an electric field which will be of a nature vanishing, because the charge carriers are decreasing. So the electric field vanishes like this, but it still remains alive within a semiconductor. So this is a case which is in middle of this and this. So within a metal volume there cannot sustain an electric field. Within a dielectric volume, a perfect dielectric or perfect insulator, there the electric field or electrostatic field will be sustained. And within a semiconductor it could be of some nature, decreasing or increasing. It depends on the charge concentration profile that we can calculate from some fundamental laws. So obviously this one is the correct option. So with this we have basically revised some basic concepts of the semiconductor theory. This is the end of this lecture number 1, and now we'll move into the much proper structured sections of this chapter, semiconductor theory. So all these concepts were the prerequisites or some brief informations to start with the major part of the of this module 1. So that will be starting in the next lecture. Thank you.